Picture this. You build a sandcastle at the beach. It looks perfect. Then someone steps near it, and slowly, it sinks. Not because it was weak. Because the sand underneath couldn't hold its weight. Now scale that up. A 10-story building weighs thousands of tons. So why doesn't it sink into the ground the same way? The answer is hiding beneath your feet, in a part of the building you'll never see once construction is done, the foundation. Here's the problem every engineer faces before a single wall goes up. Soil is not steel. It's not concrete. It's a mix of particles, water, and air pockets that can compress, shift, or wash away under pressure. If you just plant a heavy building on top of untreated soil, gravity will do exactly what it did to that sandcastle. Slowly, unevenly, the structure sinks. So how do you stop thousands of tons from pushing straight through the earth? You spread the load. Think about walking on snow. If you wear regular shoes, you sink with every step. Put on snowshoes, and suddenly you can walk on top without sinking. Same weight. Same person. The only difference is the shoes spread your weight over a wider area. That's exactly what a foundation does for a building. It takes the concentrated weight of columns and walls and spreads it out over a larger area of soil, so the pressure on any one point is small enough for the ground to handle. But here's where it gets interesting. Not all soil is equal, and that changes everything about how a foundation is built. Engineers first test the soil. They dig, drill, and sample it to find out how much load it can safely carry. Sandy soil behaves differently from clay. Clay behaves differently from rock. Some soils compress under load for years after construction. Others barely move at all. If the soil near the surface is strong enough, engineers use what's called a shallow foundation. Picture a wide concrete pad sitting just below ground level, under each column, like a flat shoe spreading the load. These are called footings. They're simple, cost-effective, and used in most homes and smaller buildings. But what happens when the soil near the surface is weak, soft, or unstable? You can't just make the footing wider forever. At some point, you need to reach down to soil that's actually strong enough to carry the load. This is where deep foundations come in. Imagine long concrete or steel columns, called piles, driven deep into the ground like nails through soft wood until they hit a layer of rock or dense soil far below. The building's weight travels down through these piles, past the weak soil, straight into ground that can actually hold it. Skyscrapers often use piles driven 20, 30, even over 100 meters deep. Without them, a heavy tower on soft soil would tilt, crack, or sink unevenly. Sound familiar? That's precisely what happened with a famous tower in Italy. The Leaning Tower of Pisa wasn't built on piles. It sits on a shallow foundation over soft, uneven soil, and over centuries, one side sank more than the other. It didn't collapse. But it tilted, and that tilt tells the whole story of what happens when a foundation doesn't match the soil beneath it. Here's the twist most people never think about. A foundation isn't just fighting against sinking. It's also fighting against movement in every direction. Soil can expand when wet and shrink when dry. In regions with clay-rich soil, this swelling and shrinking can crack a foundation over time if it isn't designed for it. That's why engineers don't just ask, how much weight is coming down? They ask, what will this soil do in 10 years, 20 years, 50 years? There's also water to consider. If groundwater sits close to the surface, foundations need waterproofing and drainage, or they'll absorb moisture and weaken over time. This is why you'll often see a damp-proof layer built into foundations, a barrier stopping moisture from creeping upward into the structure. So the next time you walk into a building, remember, everything above ground, every wall, every floor, every window, is only possible because of an invisible decision made before construction even started. Someone tested that soil. Someone calculated exactly how wide, how deep, and how strong the foundation needed to be to carry the entire building safely, for decades, without sinking, tilting, or cracking. That sandcastle didn't have an engineer. Your building does. And here's a question worth sitting with. If the foundation is the most critical part of a building, and also the part no one ever sees, why do so many construction shortcuts happen exactly there? That's what we're uncovering next. The hidden mistakes at foundation level that cause buildings to fail years later, long after everyone's forgotten what was buried beneath the first pour of concrete.